Okay. So, welcome to unit number 5 of the module on addressing mode, instruction set and instruction execution flow. So, till now basically we have mainly concentrating on what is a basic instruction, how it looks like and how it basically executes. Now, from now onwards we are trying to go in more depth of basically how our instruction works, how it is designed, how it can be clusters, what are the different type of sets in which we can club them, etc. So, in the last unit we basically saw about what is the basic instruction format, that what it has. It has a opcode, different maybe depending on the instruction format it can have 1 address, 2 address or even 0 address. Now, in this this unit basically on instruction set we are going to see in more depth of how the instructions can be clubbed based on their functionalities. So, this is a small module, it is a small unit of the module, in which case we will try to categorize the instructions based on their functionalities. Many times we have discussed while discussing in this module that it can be of arithmetic type, logical type or data transfer type, but in this case we will look into more depth of those classes, and basically what if you are executing an instruction, what are the different registers that are set. So, slightly in more depth we will go in this. Okay. So, in this case basically what is this unit summary about? So, in this unit basically we will be classifying the instruction based on their functionalities, and in each class what are the different type of instructions available we will be looking in depth. So, basically first is a data transfer. We all know that if some instructions like load, store, etc. transfer data from and basically based on one memory location to other. The memory location can be a register, it can be an accumulator, it can be a memory location in the main memory, and it can be a cache. So, anyway we are not concentrating on the cache that way, because already we have told you that in between the registers and the main memory there is an element of memory called cache, in which case wherever you want to execute some code, a part of that main memory where you are going to execute or the temporal data are loaded into the cache. So, you can easily access them because the cache is inside the processor. But anyway that we will take in more details in a future module on memory. So, basically for us right now the classification of instruction of data transfer means you have to transfer data from one memory location to another. And then in the last unit we have seen that how many such operations can be done in an instruction depends on the number of addresses. If it is a 3 address, then we can have more number of data transfers corresponding to a 2 address and so forth. So, basically what happens in this case? So, it has to calculate the address of the operands based on the addressing mode. So, if the addresses, then actually those things will be detailed out in a future module, then basically you first find out whether the value of this memory location is available in the cache, and if it is in the cache you can directly fetch it, and if it is not in the cache then you have to read from the memory module. But in fact this will be dealt in more details in a future module as we have discussed, not just told right now, but in our as of now we have to just understand that it is a transfer of data from one memory location to another. So, as I told you we will be going into depth of basically, or we will look into the more details of what are the exact type of memory such type of data operation data, or means what do I say, that is data transfer based operations. So, basically we have store. So, transfer one word of the transfer word from processor to memory, that is some operations you have already done in the processor and you store the result to a memory. So, that memory is generally a main memory, sometimes it can also be a register. There is something called load fetch, that is you actually transfer the word from memory to a processor. That is a processor register, it can be a processor register or an accumulator. Exchange, such type of instructions are also there in which you can swap the contents. Clear, reset, set and reset are also very important operations, that there are some instructions which you can make all the values of a memory location 0 or 1. So, set and reset are also a class of operations which fall under this set. Push and pop, as I told you, that you have to push a value to a register stack, and pop a value from the stack is also falls in the class of data transfer based or data operation or data movement based instruction. So, that is the data transfer based instruction. So, as I told you that push and pop basically corresponds to a stack based machine or a 0 address based instruction. Next is basically the arithmetic. So, as I told you that all we have been discussing throughout in many of the units over here, that there are 3 types of basically main the heart of all the computation is arithmetic and logic. That is, you have to add 2 numbers, you have to multiply 2 numbers, that is all the mathematical operations like add, subtract, multiply, divide, absolute, negate, increment, decrement. So, whatever things are, whatever we know about standard mathematical operations, all the instruction sets or the instructions dedicated to it will be called as arithmetic operation. But again, as I highlighted in the last unit, that add can be of several types. That add immediate, that means you will have to add the value of one operand will be available in the instruction itself. Add 2 memory locations, value of the 2 memory locations will be loaded. Then it can be add indirect. So, the idea is that even for add, subtract, multiply, at each particular operation also, there can be a lot of variations, as simply add immediate and add from memory. Immediate means the operand value will be given in the instruction itself. So, each can have a lot of different variations itself. Increment 1, increment, decrement, increment by 1, increment by 2, they are quite standard, like negate, absolute, they do not have much variations, but like add, subtract, multiply, you have lot of variations. Next is basically the logical one. Logical means they are mainly basically bitwise operation. So, like and, or, not, exclusive, or. Then actually very important, these are the standard ones, but there are some important ones like left shift, right shift, compare, that is this test and compare. Actually these things are very important, as we will see more on the in the future module, future unit we will be looking at the jump instruction or conditional instruction execution. So, in that case actually test and compare, this will be very, very important, that whenever some operations are done, some mathematical operations are done, basically some flag values are set. So, you can test those flag values, that whether the 0 flag is set, then you take a jump instruction. You compare to arithmetic operation and then set some values. So, if you compare two values like comp A comma B, that means compare the register value A, register value B. If they are equal, some flags will be set. So, this type of instructions basically fall under the category of a logical instruction. Like and or not are basic logics, left shift, right shift are very simple, test and compare are very, very important logical instructions which will be used for execution of jump instructions mainly. Then some control variables can be set for some kind of protection purpose like interrupt, etc., which will be dealt in later. Or in a nutshell, these are some of the instructions basically which fall into the class of logical instructions. That is, till now we were saying that and or not are mainly the logical instructions, but apart from the basic ones, these are other very important logic instructions. And then there are some instructions called IO. Generally, many of the cases we say that the IO is a part of the data transfer operation, but for many cases we can also classify them as input output. Basically, you read from some port, you write from some port, that is the input output devices are available. So, there will be a whole module on IO which will be taught by the other faculty members who are dealing with the courses. So, in that case it is more or less a data transfer, like input is read, output is write, but in this case it will not be exactly from a memory. So, it will be from some output devices, like it can be a mouse, it can be a keyboard, etc. So, there will be a full unit dedicated to that. Maybe I can say start of IO, that will say that I want to read from the keyboard. So, there will be one instruction for that. Test and IO, so whether the device from where I am going to read or write is functionally proper or not. So, there is another full sector of the operations or instructions basically which are dedicated to IO. Sometimes till now means as there is a separate unit dedicated for IO. So, till now we are not discussing much about input output, because sometimes in a very broad sense or an abstract sense we can also call it the data transfer operation, because you are going to read, you are going to write, start can be a control instruction, test can be again a control instruction, or it can be a in fact logical operation, you can tell like that. Read write from a memory is very simple a data transfer operation, but when you are talking to some input output devices it will be a IO instruction. Like start and test IO can be control, or you can think of logical. But when you are talk about specifically about connection to other devices apart from memory, then actually it is an IO instruction. So, this part will be dealt in more details in a future module on IO. Then the last part actually of this classification is the control instructions. As I told you, so generally the instruction goes in sequence, but based on some conditions of an operation, some flags may be set. Based on the value of the flag, you can take the next instruction or some other instruction, that is the conditional instructions. Important conditional instructions are branch, that is unconditional, load this PC with the specific address wherever you want to jump. Conditional means you have to check the value of the flag, if it is true you take that location, either you continue as procedural next step, jump to subroutine. Basically, if there is subroutines in the code, you jump to that procedure. Return means after completing this subroutine or the inter-subsys routine ISR, you go back to from where the procedure was called. So, in that case, all the values of the PC etc. has to be brought back from the stack and it has to go. Some other instructions are skip conditional, that is next instruction may be skipped, next instruction may be skipped on some conditions. So, basically these are in a nutshell the broad classification of conditional instructions: jump conditional, jump to subroutine, return from the subroutine, skip an instruction based on some condition, and halt. Halt is also a very important control instruction where you stop the code. Again, as we are discussing everything from a pedagogical perspective, so again this is basically a recall and a knowledge based kind of an objectives. Mainly in this case, you will be able to, after doing this unit, you will be able to discuss the different type of operations inside a processor, mainly between a processor and a memory. That is your data transfer operation. You will be able to explain about the arithmetic and logical operations. You will have some idea and you will describe about IO handling system and control operations of a processor. You will be able to describe the basic idea, and in fact a separate module we will discuss in depth. And comprehension means here you will be able to discuss how to program a processor in a machine level assembly language and high level languages. Basically the idea is that after doing this unit and also from the knowledges of some of the previous units, you will be able to tell that given a code, a high level code, what will be the assembly language level, what will be the instruction at the assembly level, what will be its binary version at the machine level, and what will be the corresponding high level. That means given a high level code, you will be able to translate it into assembly language and a machine language and discuss how it basically executes. So, as I told you, this unit is basically, you can think as a second part of the last unit on the whatever the instruction set. Basically we are discussing on the instruction format. So, these last two units, that is, I'll tell you. So, in fact if you look at it, so instruction format and instruction set, you can call that they are the two small units. There one is covering about the different formats, and this unit is talking about the basic classification based on some operations. So, in fact that is why, without going into much more theory in this unit, let me give you in more details by some examples that will set the that will make you help in understanding more on this units. Basically because most of the theory related to this unit has been discussed in the last unit when we were discussing about the instruction formats, because formats means what are the basic structures or what are the basic components, and here we are discussing on the instruction set how to classify based on its functionality like data transfer, IO, control or arithmetic or logic, right. So, we take a very simple example, like there is two memory locations, FF0 it has 5 and FF1 has the value of 7. We have to add these two numbers and the resultant has to be written in a memory location FF2. Okay, so already such type of program we have discussed in a previous lecture, previous unit, but here we are going to look at it more from the perspective of the instruction set and instruction format, as well as also we will look at how the memory is handled and how internal registers are handled and what are the control signals. As we will deal a same type of program now in more depth from the architectural concept as well as the instruction format and addressing mode concept. Okay, so we are saying that the job is simple, two memory location have two values, you have to add them. So, obviously the first instruction, and here we are taking a format. What is the machine type? The example we are solving here is a single address instruction. So, as I told you, the same code we have seen maybe in a previous unit, but now we are going to focus more on it from the last two units, the current unit and the last unit perspective, that is on the addressing mode and the instruction set. So, the first one is LDA, that is load accumulator FF0. So, that means whatever is value is the memory location FF0 will be loaded to the accumulator. So, this is a data transfer instruction as well as it is a single address instruction. The single address because, and as I already told you, single address instruction means one of the operator or the operand is basically the operand is basically accumulated. So, it is done. And as I told you, whenever, one thing I missed to tell you basically, so whenever you are writing a code, you have to assume what is the instruction or the machine type. So, for example, in this case we are assuming that the architecture or the CPU or the machine type is a single address format. So, in this case one is de facto a accumulator. Then we are saying add FF1. So, what is it? Is a arithmetic operation, arithmetic instruction. So, it says that whatever is in the value of accumulator, that is value 5 which was for FF0, will be added to the value which is available in FF1 and it will be stored back to register. Finally, you have to store the value of STA FF2, that is the value of the accumulator, you have to store it to FF2 memory location. So now accumulator has 5 plus 7, so it will be stored over there. So to do this operation, we have two IO operations, two data transfer operation, and one is a arithmetic operation. And this machine is a single address machine. Now, as I told you, so that now if you look at the machine code. So as I told you, machine code is always a binary code. But generally what happens, we do not write it too much in the textual literature or the books or the slides, because it becomes very difficult to read and understand. So we will give you a feeling. So what it says load FF0. So single, so this is for the opcode and this is for the operand. Single address, so that is de facto is the accumulator, which is not mentioned. So maybe I am telling you that maybe this machine has 3 instructions, so I think 2-bit codes were enough to do this, but then let us assume that the machine has some more, it has 16 operations to do, so they have kept 4-bit as the size of the opcode. So the 3 codes for LDA, store and load, add and store are this one. That is the opcode is 000 means that it is a load instruction, add means 1000, add 001 for store. And then this is the from where you have to load the value, it is FF0, so this one is going to be the binary. So if somebody erases this and say this is your first line of code, 000, very difficult to read and understand, therefore we always keep the mnemonics. So in this case the instruction size is 4, the instruction size is 4 plus 12, that is 20 bits. 16 bits, 16 bits, 4 into 4, 16 bits. So, it is a 16-bit instruction size, and you can also think that the memory in this case is a 16 word bit is a word size. So, it will be all the instructions mainly in this case, whatever is discussing for this example are loaded in a single word. So, it is easy to fetch, decode and execute. Next is as FF1. So, same case, now you can see that this format has means the code has changed where it corresponds to add, and this one is the case similarly for storing this one. So, the idea is that if I write only in these 3 binary numbers, it is very difficult to understand, so you always go for the mnemonics. And as it is again a single, all the 3 instructions are in a single address format, so the last 2 are basically data transfer and this is the arithmetic. Now, we see stepwise basically what happens. Now, we will again deal with, we have already discussed a similar example beforehand, but now we will see in more depth of the different instructions, different registers and the formats. So, as I told you, so this is the first instruction to be executed. So, the PC is going to have the value of this one, value of the memory location of the first instruction. Then what happens is that, so in this case, so this instruction, now as I told you, we are assuming that this is a 16-bit size. So, each of this memory location has a full instruction. So, only one word can be taken to the memory buffer register or the instruction register and your job is done. For example, in this case this is a single address instruction. So, assuming that if it had been a 2-word instruction, a double 2 address instruction. So, in this case you might have taken a longer side. So, maybe 0FFF and in this case maybe the other part of the other address would have been there. So, in that case you would first require to bring this taken to IR, maybe the IR would also have been elongated over here, then this part of the instruction will be taken from memory buffer register to the IR, it will be a longer case and then only you will be able to, after 2 memory read operation you will be able to understand the meaning of the instruction. If it would have been something like say I allow add memory location FF0, memory location FF1. So, in this case 0FF0 would have been here and in this case it would be FF1. So, you have to first read this, then read this part, this memory location, of course 8 would have been there, merge it and then do it. So, it will be more difficult to do that, but your instruction you would have requested only 1 or 2 instructions to solve it, but now we require 3 instructions because we are taking a single address format. But single address, these things are very simple because every memory location has a single instruction. So, what is the case? So, if FF0, so this has to be fetched. So, 3 is a load operation, 0 is a load operation from where I have to load. So, from FF0, that means it is saying to load the value whatever is available in FF0, the value of 5 to accumulator. So, first step what happens, the PC is pointing to this, this instruction is loaded to the memory buffer register, and as we know that because of this addressing format each memory location has a single instruction. So, need not worry, directly take the value of memory buffer register to the instruction register. So, it will decode it and it will find out that it is asking to load the value of FF0 to accumulator. So, that is what is being done. So, it is loading the value of FF0 to the memory buffer register and then to the accumulator, and the value of PC will be incremented by 1. Next, what happens? So, what is the value of FF1? So, it says as add value of accumulator to whatever value is in FF1. So, in fact, again as I told you, one word is enough to take a full instruction, one address format. So, it will be loaded in the memory buffer register, it will go to instruction register, decoded, and it tells that FF8 FF1 means whatever value is in FF1 has to be added to the accumulator and stored back to the accumulator. So, this one is done, memory buffer register, it is to the instruction register, it is decoded and it knows what to do. And you can understand that program PC is actually, program counter has changed to next instruction to be executed. Now, so as I told you, the next step says that you have to add this one was the step that you have to add the value of the accumulator to FF1. So, 5 was initial in the accumulator, now 7 has been to the memory buffer register, you add these two values, that is 7 plus 5 is 12, that is C, and will be again stored back to the accumulator. This is the job which is done by the second instruction. And finally, what happens is that next you have to store. So, this is the program counter has gone to the third instruction, it is getting loaded over 1 FF2 to the instruction register. So, what it tells that whatever is in the value of accumulator, because 1 means store, to FF2. So, accumulator value will go to memory buffer register and it will be stored over here. Right. So, this is the final execution. So, what we have seen in this case? So, in this case we have seen that as the instructions were a single address instruction and the size of the memory was we have assumed to be 16 or something. So, it fitted and very easily one instructions could be fetched and it could be decoded and the job be done. But if you would have taken two number of instructions at a time, so sorry double 2 address, then we could have saved on the number of instructions, but in this case you have to take this word and this word, join them and the instruction register, decode and do it. So, that would have been a more complex way of solving the problem. And again we have seen that what happens basically. So, in this first was the memory operation, memory data transfer operation. So, in this case the data is transferred from the main memory to the memory buffer register and then it goes to the accumulator or it goes to the instruction register depending on the case. The next was a address arithmetic operation. In this case what happens? So, it takes some values from the accumulator and the memory location and it actually operates, it uses an adder to add it and store back the results. That is happening in the third step, which is again a IO operation. Now, basically now we will so that was more or less whenever we talk about the arithmetic operation, ALU is arithmetic and logic unit is involved. Data stored and IO. So, control means what? Is very simple. Control means based on the value of some of the jump instruction, the value of the PC will be changed. Like for example, so if you look at it, so what happened? So, the first case the value of program counter was this, the next the value of program counter is next 3F1 and after that the value of program counter becomes 3F2, that is it goes step by step. Now, what happens? It can happen that if there is a conditional instruction, then instead of going incrementing like 3F0, 3F1, 3F2 at some point of time it will change. So, that is simple. So, if you have a conditional instruction, the value of PC gets changed. If you have an arithmetic instruction, what happens? An adder or a multiplier or subtractor is used. Important are where lot of complicated registers and control signals are used are the memory operations and the IO operations. So, the memory operations basically we will be dealing with here in details, and for the IO operations as I told you, you have a separate module on this because IO is a more complex operation, because in that case you will have a separate device which is connected to the CPU. It may be a camera, it may be a keyboard, it may be a mouse. So, you have to first understand whether the mouse is correct or operationally fine, whether it is ready to give the data and so forth. Like it's in case of a keyboard where it says that I need a data, then you have to wait till a person presses the keyboard, then I press the keyboard, then again the data comes. So, a lot of synchronization issues. So, a whole module is dedicated to that. But right now we will see what is the memory fetch operation, how it interacts with the memory, what are the addresses involved, what are the registers involved and what are the control signals. So, memory fetch means memory read. Okay, because the other class of instructions like data transfer as well as your control are quite simple. So, what happens whenever you want to fetch a memory location, you have to give the value in the memory address register. So, whatever value is given in the memory address register is the location from where the data has to be read. The MAR is connected to the memory bus and hence the address is required for this one to the main memory. So, MAR basically is connected to the to the memory address register is connected to the basically address bus of the memory, and so it is therefore you directly memory will get the value of the address from there. Next, the CPU has to tell that it is a read operation, because we are at present discussing about memory read. So, there is a control line, we have already told it is read or write, it tells the control line says that it is a read operation. Now, actually there is a difference between the CPU speed and the memory speed and the IO speed. CPU is the fastest, memory is slightly slower, and IO is extremely slower, because IO means myself, you and some human being is handling. Memory is a slower device compared to a CPU, that we will see later, but for the time being you can consider this hierarchy. So, therefore, there is a synchronization issue, that whenever I say that I read from the memory, but you are never assured that immediately I will get the answer. So, there is a synchronization issue, that is a handshaking, that you say that I want to read some memory location. So, I give the value in the memory address register, and then the memory address register via the address bus is connected to the memory. Then you say that read, so the read signal is made. But how much time I should wait before I take the value from the memory buffer register? Because based on your read and the address in the MAR, the data will be saved in the memory buffer register. So, there is actually the CPU waits till receives an acknowledgement from the memory, that is memory function complete, MFC. So, MFC is a very important control signal. So, what it says that whenever a job is done, that is read is done, data is dumped to the memory buffer register, it will make the MFC signal high, or maybe it will say that it is enabled. So, now what will happen? You have to read the value from the memory buffer register and you can freeze the location therefore. So, that freezing etc. will come later, but for the time being, whenever you say that I want to read from the memory and the data is available in the memory buffer register, and then you have to wait till the memory function complete is set to 1. Once it is done, you know that the value is stable in the memory buffer register. Now, it can be read to the accumulator, it can be read to the instruction register and so forth. So, next is basically the memory write, but let us first this is the memory write, we will come to it later. First let us see basically a memory fetch operation in the steps as well as in the pictorial representation. As I told you, first it is in the memory address register, then read, then you wait till the memory function complete is ready, then when it is done, then it can be read to the memory buffer register, or it can be register 1, accumulator or wherever, and then only then actually the memory buffer can be is ready, you read it from this one and then you can go ahead. I will better take it a figure and explain it. So, what was the example? The example they are saying that data 7 hex which is available in memory FF20, we want to bring it to CPU register R0, that is the example. And typically this is a flow, whether you want to take it to accumulator or any register, this flow more or less will become similar. Is the accumulator, the memory buffer will write to the accumulator, if it is R0, the memory buffer will register write to R0. So, now let us see step 1. So, I want to read from this memory location FF20. So, memory address register will have the value of FF20, this is connected to the address bus, it is gone. Then I want to read this basically. So, now next step is read signal is given. Now, you have to wait. How we have to wait till memory function complete is 1. So, once the memory function complete is 1, it means that the value of this one is written to the memory buffer register and it is stable. So, once that is done, in step 4 you have to freeze it. Many times I was saying what is freeze. So, freeze is a very simple operation. If I take a D flip flop, DQ is a D flip flop, if I connect D back to Q. So, if I can connect D back to Q, therefore, there will be no change in the value of D even if I apply a clock. So, that is actually a freeze operation. So, if I make a permanent connection like this, so your memory D flip flop will always have the same values. Actually, what happens is that there is basically a multiplexer and this is D and this is Q. Sorry, this is D and this is Q. Maybe one port will be freeze, another port will be load, and this will be a mux. So, if you make mux is equal to 1, then from the port it will read to D and your flip flop can be set and reset. And if I make this mux value equal to 0, then the Q will be feedback to Q, sorry, Q will be feedback to D, and there will be a loop back and it will be in a freeze position, that the value will never be stabilized. So, this is actually multifunction register, so you can read over it from the digital fundamentals. So, basically in step 4, after the MFC is ready, you freeze D, that memory buffer register is freeze, the value should not change over here. That is, even if you give a new memory address, you say read MFC 1 or whatever, the value of memory buffer should not change. And then in this step 4, you freeze it and load the value in the register R0. So, once it is done, in step 5, you can release the freeze. So, what happened? Step 1, I give the address, step 2, I say read, then I have to wait for synchronization that the memory function is complete, After it is complete, you read the memory buffer register. So, at the same step, when you are reading it, before the actually after reading it, you have to freeze it, or you can say just after step 3, when the MFC has been 1, you freeze the memory buffer register. That is, you do not allow any more changes to write over there from the memory. That means, even if I give a new address line and if I give a new step or whatever, this value should not be disturbed. And then in the step after freezing it, you read the value of memory buffer register to your required register, which is R0 in this case, it can be an accumulator, and then after step 5, you defreeze this, and again the step repeats basically. So, that is what I was saying, that in this case generally registers have freeze, load, all these commands are there. So, after basically the memory says that MFC, so generally we freeze the in case of read we will freeze the memory data registers, or also for many cases we will freeze the write and read registers from the memory. So, the data corruption because of race conditions do not happen basically. So, we are discussing in details for that memory data transfer operations from the memory, because it involves many more critical steps, as we have seen. It is not just like giving the address and getting the value, there is a lot of synchronization involved. Similarly, the memory write register is also very similar, but in this case what should happen is that in this case you have to give a write command. First you have to give the memory location value, then you have to give the write, and then you have to again wait till the memory function is complete. That means, the memory says that I have been able to successfully read the value from the memory buffer register. But again, after you put the, so what are the steps? So, step is that first you give the value in the memory buffer register, then you say that you give the memory address, or you can change the phase, then you say write. Before you give the write signal, your data to be written to the memory has to be stable in the memory buffer register, and then you have to wait till the memory said that memory function complete, that I have already read the value from the memory buffer register. But once the memory starts reading, you have to again freeze the memory buffer, and then only you can release the freeze only when after it says that the memory has been read from the memory buffer register. So, there is again a synchronization involved, that is, whenever the for the time for which the memory is reading from the memory buffer register, it has to be freezed, and you have to wait till it says that the memory function complete is equal to 1. Then you can again defreeze and go for the next value. So, again this is the same example. It says there is a data 8F in hex which is available in register 0, and you have to store it in memory location FF. So, place the address in memory buffer register, then transfer R to MBR, and now memory buffer register has to be freezed. That is what, first you locate in the memory address register, you put the value 25FF, that is I want to handle this memory location. Then you put the value of R0 register or accumulator, whatever may be the case, in the memory buffer register, and then you stop the memory buffer, that you freeze it, because now the memory will start reading from the memory buffer register. Here if now the memory buffer changes, then there can be always a race condition and some garbage value may go into the memory. So, you have to have a freeze control signal. So, you freeze the memory buffer register, and then you activate write, and then you have to wait till the memory says that MFC is 0. That means, I have read the data correctly from the memory buffer register. Now, you can remove the control signal, you can defreeze everything and go for the next operation. So, this is the example. So, always first step in general any memory operation will be the value of the memory address register. Then in step 2, you bring the value of from register 8F to the memory buffer register and freeze. That is very important. This one you put over there and you freeze this whole step. You basically freeze the memory buffer register. Don't allow any changes there. Now you say give write signal. Then write signal means it will start reading from the memory buffer register. But note here that the memory buffer register is now freezed. So if the memory buffer register is freezed, no, whatever may be the changes over here, it will not be changed, and memory will very nicely read the value, that is 8F will come over here, and after 8F will come over here, it will say that memory function is complete. One memory function is complete, you can defreeze everything and go for the next memory cycle. Okay, so in a nutshell, this was a very small module in which we have showed you the classification of different type of instructions based on the functionality, and then one of the most integrated form of instruction, that is the data transfer and IO. So, IO will be dealt in a detailed manner, but in the current unit we have shown you in a very detailed manner that basically how a input output operation happens, what are the synchronization signal involved, and on that class of instructions how the memory and the CPU is synchronized, and what are the detailed memory involvement and the registers involvement in that. Okay, so as I told you, these were the basic objectives which we are targeting in this unit, that you have to basically describe what are the different type of instructions, what are logic and different type of arithmetic operations, control operations, etc. A very simple question, if I say that I want to evaluate some expression and I say that the values are available over this memory location. Then I ask you, you write an assembly language code and very precisely show how the memory type of operation happens, write an assembly language code for that, then very explicitly show that in different type of modes how the memory is accessed, how the synchronization happens, and also show the different type of register values. So after listening to this unit and the units previous to that, you will be able to solve this problem. Here you will be able to design the assembly language code, then maybe translate it into machine language, but anyway that is not very easy to read, so we keep the mnemonic version. Then you can see that there will be lot of memory read and write operations. So how they will interact with the memory. So basically you can talk about the I/O handling. In this fact, actually I/O means a memory in this case basically, because I/O we are not directly dealing with, they have just given you the idea. So basically different type of logic operations, different arithmetic operations will be happening over here. So you can get a great deal of if you are able to solve this problem. So most of these knowledge based and explanation based, comprehension based objectives will be solved. I mean objectively can be met basically. So with this we come to the end of this two basic modules or basic units, sorry, basic 2 units, in which case we have seen an instruction, these components of an instruction and how they can be classified. So next unit will be a more dedicated unit and will be an elaborate unit on which we will show that, as I told you, add instruction. Add instruction can be very different type. Add can be of immediate, it can directly take from a memory, it can take from one from a memory and one for a register. So how the different type of instructions, how different type of instructions for a same operation happens basically. That is in more depth of how the instructions can be curtailed, so that it helps you to solve the same problem in a more efficient manner. Like add, the data can be from the instruction itself, and if you will require a very wide data or a very precise data, you have to store it in multiple locations in the memory. So same instruction will be doing the same operations but in a different manner. So that is different mode of addressing modes will be there. So next unit will be more dedicated on a more rigor analysis of different type of instructions. Thank you.